So hi everyone, so my name is Youssef. I work on SNARK at ConsenSys. So I'm also doing a part-time PhD in parallel. So I'm going to talk about pairings in L1CS. So we had this presentation, if you were here before, on arithmetization, so including L1CS, so that's cool. So I'm going to talk about, just some preliminaries on SNARKs and pairings, and then some motivations why we would like to write pairings in L1CS, and then how we did optimize the pairings, so the number of constraints of this circuit. So here I just gave two examples of Gauss 16 and Planck. So what is most important for us is the proving time. So basically, if you reduce the number of constraints, then you reduce the time to generate this proof. So this is why we want to reduce the number of constraints. Bilinear pairings are, this slide is just for notations. So you have an elliptic curve here given in short Weierstrass form. Defined over some finite field of prime characteristic or a power of a prime, and it has a subgroup order which is a prime. So it is pairing friendly. It means that it has an embedding degree which is not too small, not too big, maybe in the range of 10 to 30. So the embedding degree is this integer k, which is defined as the smallest integer, such as the subgroup order R divides Q to the k minus 1. So a pairing is a bilinear map that goes from G1 cross G2 to some target group GT. G1 and G2 are defined over elliptic curves. So one over the finite field, the other over some extension. And GT is also a group of order R, but this time it is defined over an extension field and not a curve. So it is, for some kind of pairings, the rth of unity. So motivation, why we would like to do pairings inside a circuit. So for example, if you take Gauss 16 proofs or Planck proofs, so the proofs are constant size, so it is a bunch of elements in G1, G2, and the verification is also a bunch of elements in those pairing groups, G1, G2, and GT. And the verification equation is this pairing equation, so this equation 1. And if you manage to verify this pairing equation inside a circuit, then you can aggregate proofs. Another application is private computation à la ZK7. And so ALIO is using this in production to have these verification keys as secrets, so that you have a universal.
It should fix itself.
Yeah. So a universal circuit. So another application is BLS signatures. So the BLS signature verification is also this pairing equation, and CELO is using in production a SNARK to prove this BLS signature. So this is another application. And finally, maybe if you want to verify KZG verification equation inside a circuit. So this is something that we are considering for ZK EVM. So when you want to do recursive proofs of ZK EVM, KZG based ZK EVM. So also the verification is a pairing equation. So why we're talking about this? Because it's not easy to do this, because we have actually an arithmetic mismatch. So the computation, so the programs in a SNARK are expressed over FR, with R the subgroup order of the elliptic curve that you use to instantiate your SNARK. The proving is also over FR, but the verification is a pairing computation which takes place in a different field, which is FQ to the K. And Q is different from R. So maybe you can take the same an elliptic curve for which R is equal to Q, but this is just the security assumption is broken. The second attempt would be to simulate operations. So this is quite inefficient in L1CS, but maybe in Planck we have more tricks. But anyway, it will be slower than native arithmetic. So we will not use the same elliptic curves, but two elliptic curves to do the trick. So what I mean by two elliptic curves, so whether we need a cycle of elliptic curves or a two chain of elliptic curves. So a cycle is, you find two elliptic curves for which the subgroup order of one is equal to the field size of the other one, and vice versa. Or maybe you just need a relaxation of this notion, which is just, you start from an inner elliptic curve, so the one in the bottom, and then you construct a curve for which the subgroup order is equal to the field size of the inner curve. So this is the inner curve, the outer curve. We will be more talking about these two chains. So we had a paper accepted this year at Eurocrypt where we construct these elliptic curves, basically for Gauss-16 applications or KZG-based applications. This is not what I'm talking about today, but what I want to talk about is these pairings. So there is a long line of research on how do you efficiently implement pairings outside of the circuit. But there isn't a lot of research, how do you implement this efficiently inside of a circuit. So our pairing is a non-degenerate bilinear map. So if you do not want to look at the equation, just look at this TZ by Diego Arana. So you have two curves. The bilinearity means if you pair A times P and B times Q with P and Q points on the curves and A, B scalars, then the output will be the pairing of P and Q to the power of the scalars, A times B. So there are many variants of pairings. So here I'm just mentioning the most efficient one, the 8 pairing or the optimal 8 pairing. So it is done in 2 steps. So what we call the Miller function, and then what we call the final exponentiation. So you just need to compute a function, and then you exponent to q to the k minus 1 out of r. So for BLS12 or BLS24, this is what you need. So what are these functions? So this is just a definition for what is a Miller function with algebraic geometry notions, but we do not care about this because algorithm-wise, we just use this trick, because at the end of the day, we do not know what is this function. We just need to evaluate it at some point p. So we use this iterative fashion. If you have so basically this equation. So which gives us this algorithm. So basically, this algorithm is an iterative algorithm. So it's a loop. So it's you take the bits of what I call the size of the Miller loop, the points Q, P, and Q, and you compute some lines and some multiplications, some squaring. So basically, it just boils down to computing some arithmetic over the curve. So here we just have doublings and additions. And over the finite field extension, we just have some squarings and some multiplications. So as I said, there is a long line of research in order to optimize those pairings. So we need G2 operations. So we do not work over the full extension field fq to the k, but we can compress the coordinate to some subfield. So q to the k out of d with d some twist degree that parameterize the curve. And then we do not use affine coordinate, we use projective coordinates, maybe homogeneous projective coordinates, for instance, because you can share computations between doublings, addings, and line evaluations. So there is a many tricks. On the finite field, you can also construct the finite field the way you want. You just need to go through fp to the k out of d because you need this for G2. And we have also some tricks in order to do some efficient multiplication in the finite field when the elements are sparse. And finally, the final exponentiation is the raising to this power fq to the k, so p to the k minus 1 out of r. So we divide this into 2 parts, easy part and hard parts. So what you need to learn is that the easy part is easy. So it's just a polynomial in P, and raising an element to a polynomial in P is fast because you use Frobenius maps. So for BLS12, it just costs a Frobenius map, a conjugate, an inverse, and a multiplication in FP12. And the hard part is more expensive. We have some tricks based on vectorial addition chains or lattice-based optimizations, but the dominating cost at the end of the day for this hard part is squarings and multiplications in this finite field. So it's only now that I will talk about our work. But it was necessary to introduce these techniques because what we want to do is we want to implement pairings for inner BLS12. So those curves are always of the form y squared equal to x cubed plus 1. So they are polynomial based, which means all the parameters are given in polynomials. So K is 12, D is 6, so GT is over FP12, G2 is over FP2, because you divide K 12 by 6. And then you can choose any tower field construction you want. But inside the pairing, we will choose the first one. I mean, the difference of performance is slightly the same. But if you use the second one outside of the circuit, you have better compression. So you have a ratio 1/3, and in the first one, 1/2. But those are details. So the point is, we need to implement this Miller function and then this pairing, this exponentiation inside of the circuit efficiently. So here are the papers, or some of the papers that best implement pairings on BLS12. So I'm not going to talk about R1CS, but what I want you to know is it's just about quadratic equations. So you just need to write whatever statement you want to prove with these quadratic equations. So this is a famous example by Vitalik Buterin. But at the end of the day, you just need to write O equal to L times R. So with all those techniques we know about to implement pairing, so pairing over BLS 12377 is just, well, less than 1 millisecond. If you just try to naively port the best optimizations we know outside of the circuit, inside of the circuit, the number of constraints will be 80,000, which is quite a lot. So the point is to reduce it significantly. So when you look at on the internet or for pairings inside of the circuits, there isn't much literature. So there is just a GitHub ticket on Zcash, and implementation-wise, there is just, I believe, ArcWorks and maybe SNARK for some other curves, MNT4 and MNT6. So ArcWorks reduced the number of constraints to 19K from 80K, which is quite a lot. And we were able to reduce it even further to 11K. So we went from 80K to 11K, basically. So how we did this is this list of tricks that I will detail. So, so as I said, the R1CS is about writing O is equal L times R. So squares and multiplications in the finite field are the same, constraint-wise, but inverses are not, because inverses cost the same as a multiplication plus one constraint. So instead of doing the inverse, you just compute the inverse outside of the circuit. 1 out of L is equal to O, and you provide O as a hint. So inside of the circuit, you just compute L times O. So you substitute an inverse by a multiplication, and then you check that it is equal to 1. Division the same. Not 1, but it is R. And also, outside of the circuit, we always do inverse plus multiplication. But inside of the circuit, we can just do division. And then we get rid of the multiplication cost of constraints. Over an extension field, so squarings are not multiplications because we have other techniques to reduce the squarings. And all the inverse and divisions tricks are the same. Outside of the circuit, we always use projective coordinate or Jacobian coordinate because we do not want to do inverses. Here, we don't care about doing inverses because they cost almost as much as multiplications. So this is the number of constraints for doubling and addings. So the doublings has more constraints than addition, which is funny because so when you do this Miller loop, so the size is fixed. So you can do an addition, a short addition chain for this loop. And short addition chains, always when we create short addition chains, we look at maximizing the doublings and minimizing the additions because doublings cost less. But inside of the circuit, it's the other way around. So this is one of the tricks. The other one is, so when the bit is equal to 1, so we do doublings and then additions. So 2R plus Q. But I said that doublings cost more than addition. So we can just, instead of doing 2 times R plus Q, we do R plus Q plus R. So it saves us 2 constraints. But then we can do even better. So in the first addition, you can just omit the Y coordinate. And this would reduce the number of constraints to 17. So from 22 to 17. And you do this whenever you have a bit equal to So the line. So the line evaluation. So the line is ay plus bx plus c. And we need to evaluate this line at some point p. So the line that goes through 2 points, or 2 points, or the tangent line. So there are a lot of tricks for this outside of the circuit, but the best one is this. So paper from Arania, Barreto, and others. So it is a sparse line, so it is an element in FP12, but we have like 3 FP2 zeros. So the multiplication is sparse. So in constraint-wise, it's so a full multiplication costs 54, but this sparse multiplication costs 39. So the trick we can do inside of the circuit is we pre-compute one out of E, so the inverse of Y and the division of X of P, so that doesn't cost 5 constraints, that does cost just one constraint, because P are over, so the point P is over G1, not G2. But anyway, so it costs just 2 constraints as a pre-computation, and then you multiply this, and the line you had is this one, so in blue. So this, if you multiply an element in FP12 with this sparse line, it costs 30 constraints. So compared to 39. So these are the tricks for the Miller loop. For the final exponentiation, so the easy part is just this code. So you do a conjugate, no constraints added. An inverse 66 constraints, multiplication 54, Frobenius square, no constraint, and multiplication 54. So as I said, you can merge inverse and multiplication. So you just, inside of the circuit, you just get rid of one. But we were able to do slightly better. So more on that later, but we can reduce the number of constraints from 174 to 60. And we can omit the decompression as well, as I will explain. But why is that? So I will move to the hard part and then I will explain why. So outside of the circuit, there is a recent paper by Hayashida et al. To implement this hard part with lattice-based reductions. So this is the code, basically, in Go. And so what is in blue is what costs constraints. The others are free constraint-wise. So it's just about squarings, so I call here cyclotomic square, multiplications, and XPT. XPT is the exponentiation by a constant. So it is always the same constant, so we can have a short addition chain for this. So it costs multiplications and cyclotomic squarings also at the end of the day. So we would like to optimize these squarings inside of our circuit. So outside of the circuit, the best algorithm to do these cyclotomic squarings, generically speaking, is a paper by Granger-Scott. So inside of a circuit, it costs 18 constraints, and a normal squaring costs 36 constraints. So there are also another paper by Carabina where we can do 12 constraints or 15 constraints, but then we need decompression, which costs 19 constraints or 8 constraints. And then there is also this Torus T2 paper by Rubin and Silverberg, where the cost is 24, and the compression is costly. The compression is costly constraint-wise. So why we would use this? But the takeaway is that if you have just 1 or 2 consecutive squarings, you use Granger-Scott inside of the circuit. It's 18. But if you have 3 squarings, you would use Carabina, the first version, or more than that so far. You would use Carabina because you amortize the cost of the decompression, because the decompression is done only once. The multiplication, so the multiplication costs 54 constraints over FP12, and in Torus-based, it costs 12 constraint less, so 42. But then you need compression and decompression. But the nice thing is that you can do T2, you can do squarings for both T2 and so Torus-based and squarings. So you can amortize the compression and decompression. You can do compression at the very beginning and decompression at the end. So you can do the whole final exponentiation in compressed form. So instead of working over FP12, we can work over FP6. And better, we can even get rid of the compression and decompression. Because, as I will show you, we can absorb the compression cost in the easy part computation. And do we really need decompression? Because in the applications I mentioned, we just need to verify a pairing product. So you just need, for example, to check that two pairings are equal. So whether you check them in compressed form or in decompressed form, we do not care. So decompression can be amortized. So we can get rid of decompression and computation amortized. Okay, definition of what is a, now I'm going to talk about Torus, so algebraic Tori. So this is the definition, if you want to read it. So so you just have this norm, but what the takeaway is that if you take an element in fp to the k, fq to the k, or fp12, then if you do the exponentiation to the easy part, then the element is in the torus. And if it is in the torus, we can use these multiplication and squaring techniques. So the T2 crypto system was introduced by Rubin and Silverberg. It was fashionable at that time because it was a replacement to RSA, but no one is using it. Why no one is using it? Because here are the algorithms to do arithmetic over torus. So there was a long line of research to do compression in finite field extensions, so XTR, Lucas sequences, but those use traces. They are not groups, so you cannot do multiplication. You can just do squarings, for instance. But then you had this paper which introduced T2 and Cayley crypto systems where you can do full arithmetic. But the problem is that, well, there are inverses. So no one wants to do arithmetic with inverses outside of the circuit. But as I said, in R1CS, well, we do not care to use inverses. So it is pretty much R1CS friendly. So when you see here, the compression costs just one inverse in FP6, not FP12. So the decompression costs one inverse in FP12. The multiplication costs just so one multiplication in FP6, one division in FP6, and the squaring costs just one division in FP6. Inverses are just a negation, so they are fair. So this is what we use, and then, as I said, we will absorb the cost of compression in the easy part. So in the easy part, we need to take an element in FP12 to the power p to the 6 minus 1, p to p square plus 1. So this is the p to the k minus 1 divided by the cyclotomic polynomial. So the simple trick is to take the numerator to p to the 6 and the denominator there. And p to the 6 is just a conjugate because we are working in FP12. So we divide by C1. So at the end of the day, compressing it is, we can merge the compression and the computation of the easy part. So it just costs one division, and then we need to rise to p2 plus 1. So exponentiation to p square is 3, and then you just need a multiplication. So the cost of doing the easy part and compressing the element is just 60 constraints. So just a multiplication and a division in FP6. So we have also further optimizations. So the point is to carry, so this is not implemented, so the 11,000 is without this. So the point is to carry the whole Miller loop in compressed form. So, but the Miller loop happens before the easy part that puts the element in the torus. So how can we do this is, well, we will just take this trick here whenever we have an element in FP12 in the Miller loop. So we will just compress it this way, and we will use T2 cyclotomic squarings and not normal squarings. And the line, so the trick for the line is, since we divided by this y, so we have the first part, so the first FP6 part is just 1. And the other one is a full element. So when you use the same trick, it's just an inverse. And even better, we won't even compute this inverse, because we will also absorb it in the computation, in the multiplication in compressed form. So at the end of the day, it will cost just a division and a multiplication in FP6. So the implementation is open sourced. It is on so it is MIT Apache licensed. So it is on SNARK, a library in Go. So an example for BLS 12377, so the number of constraints is 11,535. So we went down from 19,000 to this. So I just give an examples of Gauss 16 verifiers, BLS signature verifiers, and KZG verifiers. So they cost 19, 14, and 20,000. So for BLS 12, it costs more than that because we have FP24, so it costs 27 constraints. So we have more optimizations in mind, not implemented. So these are the to reduce the number of constraints even further. Finally, so you can try the code in this playground, so play.gnark.io. So I don't have Wi-Fi. Yeah, but the idea is we have a playground in Gnark where those examples are pre-built, and you can do Gauss 16 recursive proofs or BLS signatures inside a SNARK or KZG inside a SNARK, and you can do this with both Plonk and Gauss 16. So the numbers I gave are for Gauss 16, but the same tricks works also for Plonk, but maybe for Plonk we will have more optimizations that will come up soon. Yeah, sure.
Time for questions?
Yeah, sure.
Okay. Here, like you optimize like the Miller loop on R1CS. There are like weird way to compute pairings, like using elliptic nets.
Yeah.
I wonder, like in that case, like the elliptic nets are not really faster than this. I wonder if it will be in any case R1CS.
No, it doesn't as well. So I looked at the elliptic
In
nets.
that case, doesn't make sense sense to use it. I was wondering if the circuit will be any better.
No, inside the circuit, so the number of constraints are more than that for a Miller loop. So there are a bunch of tricks that works outside of the circuit as well. So if you notice, I just cost this one. So this is a recent paper by Patrick Longa from Microsoft to do multiplications outside of the circuit, and he managed to reduce the number of the time for a pairing. For example, also on Ethereum, so for the BN or the BLS12, but inside of the circuit, it increases the number of constraints. So I've looked at some tricks that works well outside of the circuit, but inside the circuit, this is what I just come up with. Maybe there are more.
Thank you.
Yeah.
All right, time for one more question.
Yeah.
If you have like a product of several pairings, will their circuit can they amortize?
Yeah, so what I didn't tell you is that, so this is the cost of just a pairing. So the Gauss 16 verifier, the BLS signatures, and the KZG verifier, it is a product of pairings. And the cost I'm giving here is not the cost of a single pairing separately, but it uses multi-pairings. So we also implemented multi-pairings tricks inside the circuit. So you can like neutralize some squarings in the Miller loop. You can also multiply the lines together before multiplying them by the accumulator. So it is already implemented if you want to look at the code.
Perfect, thank you.
Okay.